Okay, so in the last class, we have derived this conservation of mass equation. Okay. And what was the conservation of mass equation we derived? It is a vector equation. Okay. So del rho del t plus del dot rho u. This was the equation. And since this equation is in vector form, this represented del can be represented in a Cartesian coordinate. It can be represented in cylindrical coordinate, and it can be represented in spherical coordinate. Cartesian x, y, z system, cylindrical r, theta and z system, and r theta and r phi theta or r theta phi system. Okay. So for particular Cartesian system, del operator is defined as del x I cap plus j cap del y plus k cap del z. Using that, you can get an expression for Cartesian coordinate, and that was, what was the equation we got? Del rho del t plus del u del rho u. So del is operating on rho u. So rho and u is defined as, here u is defined as iu jk plus w jv plus wk. Rho v y and rho w rho z equals to 0, with u is equals to I cap, and this is the magnitude, this is the component of u in I direction, component of velocity u in y direction v, then component of velocity in g direction, that is w. So you got this equation. Similarly, in cylindrical coordinate, you got equations, and also in spherical coordinate. So to get cylindrical and spherical coordinate, you can use the definitions of relationship between x, y, g and r theta g. Okay. if you know x, y, z and relate with r theta z, then we can convert these Cartesian coordinate system, these equations into a cylindrical equations, cylindrical coordinate equations. Okay. So I'll just write those equations in cylindrical coordinate. In cylindrical coordinate, equations conservation of mass equation becomes del rho del t plus del r rho u plus rho u r plus 1 by r del rho v del theta plus del rho w del z equals to 0. And in spherical coordinate, del rho del t plus 1 upon r square del r r square rho u plus 1 over r sin phi del phi rho v sin phi plus 1 over r sin phi del rho w del theta is equals to 0. Okay. So while defining this, in case of cylindrical coordinate system, we have used this relationship between x and y and z. For this particular case, x is equals to taken as r cos theta, y is taken as r sin theta, and z as taken as z. And in this case, x relationship between x and theta cos theta and phi is taken as r sin theta cos phi, y equals to r sin theta plus sorry, not plus, sin phi, r sin theta, r sin phi. And z is equals to r cos theta. Okay. Okay. Now, what is the physical meaning of this? Okay. So, what is the physical meaning of this equation, for example? All the equations are same. In all the equations, you have same meaning. But Cartesian coordinate system equations are easy to follow. So, del rho by del t in the first term shows Suppose this is a system, for example, then in that system, what is the change of this rho in this system with time? Okay, at t is equals to 0 at t. So locally, what are my changes in the rho? Okay. So if anything is addition of mass is there or some mass source is there, then those things are happening over a period of time, then those will be reported in this. So this is a local change. This you can say a local change, rate of change. Okay. And this is what happens at uh, the boundaries. Okay. Del x represent del x, del y, del g. What happens in the spatial directions? Okay. In the spatial directions, you can say. So this is a local, and this is a flux, you can say, net outflux. Plus del rho v del y plus del rho w. Here rho is missing. Rho w del g equals to 0. This part is a net outflow of mass. Okay. Now this equation can also be represented if you now this particular form is called as conservative form. Okay, this form is called as conservative. When all these variables are within the derivatives, then they are called as conservative form. Okay. Now we want to convert this conservative form into non-conservative form, and using some special property, we want to simplify this equation. Okay, that is the purpose. So to do that, we just expand this del rho del t plus, then what will be there? U del rho del x plus rho del u del x, right? So I'm writing that term later on. V del rho del y plus w del rho del g plus del u del x, rho del u del x plus rho del v del y plus rho del w del g. It is simply a product rule used here and expanded. Now from the definition, we know that this d rho del rho by del t is nothing but d rho dt. Okay, plus this term rho del u del x plus rho del v del y plus rho del w del g equals to 0. And from the definition, if rho is constant, for constant rho, if rho is constant, rho is equals to a constant, then a derivative of the constant is d rho by dt of a constant is 0. So this term goes. And what do you mean by rho is equals to constant? This is a special case where the fluid flow, the fluid is incompressible. The fluid is incompressible. Okay. So for incompressible fluid, we can write the continuity equation or conservation of mass equation as rho del u del x, and since rho is common or constant, you can take it out, del v del y plus del w del z equals to 0, and since rho cannot be equals to 0 since it is a constant, del u del x plus del v del y plus del w del z will be 0. So we finally write in a simplified form del u del x plus del v del y plus del w del z equals to 0. This is for 3D flow. This is for three-dimensional flow. Three-dimensional means you have a Euclidean system where you have three dimensions x, y, and z. Now for 2D, this problem can be simplified 2D and incompressible. This is also incompressible. Okay, incompressible. For 2D problem, you can say del u del x plus del v del y. 2D means I'm just saying I have only x and y. Not needed x and y, it can be y and g, it can be xg, it can be any combination of two axes. Let us say we have x and y, so del u del x plus del v del y is equals to 0. Okay. Now what is the physical meaning of this? Del u del x del v del y is equals to 0. So okay, so suppose physical meaning. Okay, so suppose we have a flow occurring in a channel. Suppose we have a flow occurring in a channel. Okay, and we just now will just focus on a small part of a domain. Okay, suppose this is x, and suppose this is x plus delta x. Similarly, I want to take some y and y plus delta y. So essentially, I'm looking at this particular cell. Now, say in this particular case, say del u del x is greater than 0. Del u del x is greater than 0. What does it mean? U at x and u at x plus delta x, suppose. So which one is greater? If del u del x is greater than 0, what does it mean? Del u del x is greater than 0. What does it mean? The value is increasing. The value of u is increasing, isn't it? Del u del x, rate of change of u with x. Okay, del x of u, change of u with x is increasing. So it means that u at x plus delta x is greater than ux. Okay, so something is coming in and some large amount is going out. Small amount is coming in, large amount is going out. Okay. So what does this means? Now small amount is coming, large amount is going out. So what should be del v del y in order to make if this is a positive quantity, say this positive quantity is say del u del x is equals to 1. Then in order to make this is equals to 0, del v del x should be del v del y, sorry, del v del y should be less than 0. What does it mean? Del v del y less than 0 means large amount of some mass should be coming in from the uh, you know y direction as compared to what is going out in y direction. Then only this sum plus this sum will be equals to 0. You got it? This sum plus this sum should be equals to this sum. Okay. So the flux in X, uh, so for so you got the meaning. Okay. So in order to have a constant mass in the system, you need to have either if your del u del x is greater than 0, then your del v del y should compensate for the change such a way that total mass of that system remains 0, constant. Okay. Okay. So therefore, del v del y should less than 0. Okay. Now with this understanding, we'll move on to our next equation, that is called as conservation of momentum. Any doubt regarding this conservation of mass?
Am I audible?
Yes.
Good morning, sir. In that, before capital D, you have written
Yeah.
capital D rho by dt.
Uh,
So that before step, we have that. So we are considering density as constant, so that u d
yes.
rho by dx, everything will get cancelled, sir.
Yes. So if you mean that rho is constant, means d by dt of rho is 0. Derivative, this is a total derivative. This is a substantial derivative. Okay. It is
Yes,
also like d by dt. Okay. But d by dt is for particle and capital D by dt is for material volume. Okay.
yes, sir.
Fluid element. We are talking about fluid element now. We are not talking about fluid particles. You understand that?
Yes,
In
sir.
the first, yeah, last class I have told you that particle approach is not used. Fluid element approach is used. Okay. Or any element approach is used. So,
Sir,
yeah.
sir, is there any point for which these equation gives infinite solution, matlab infinite as a solution?
See, if you have these two variables, if you look at this first equation, how many variables are there? Two variables. And how many equations we have? Only one. Is it a solvable system? Is it a solvable system? No. Okay. So in order to get these solutions for UV, you need some more equations, and those equations are going to come through conservation of momentum, and those we are going to look at. Okay. So what was our RTT? What was our RTT equation? We are going to use RTT in its full form for all our derivations. The RTT equation reads like this: d phi by dt, or our now for our case, as we said, we will say d by dt, is equals to integral over a control volume del t rho phi d. Now I am writing volume V plus control surface rho phi u dot n ds. This is our RTT. So to get the momentum equation, we have to conservation of momentum. So we are now focusing on momentum, and then we need to define this fees. Okay. So let P, I mean, these are not let, but these are fees. P is nothing but momentum, mu, and small phi then becomes only per unit mass, so only u. Okay. And we know from the from Newton's second law of motion, Newton's second law of motion, we know that this d phi by dt is nothing but equals to a force. Okay. D phi by dt is nothing but equals to a force. And this force is an external force, is it? This is an external force. And there are two types of forces. Okay. There are two types of forces, F external. We generally consider those are body forces and surface forces. F body plus F surface. Okay. Now, body forces are through gravity. Okay. So it completely throughout the volume. It completely acts throughout the volume, like gravity force. Surface forces acts on the surfaces. Okay. So like pressure, shear, these are the examples of surface forces. So suppose let the chi is a body force, let chi is a body force per unit volume. Then F body can be written as chi dV. Okay, V is a volume. V cross is a volume. So a body is, now we have some expression for a body. Similarly, to get an expression for surface forces, consider a surface, okay, like this. Now on this curve, since this is a curvature surface 2D, we may have uh, forces like, we may have a normal force sigma xx. We may have on this plane, we may have sigma xy, and here we may have sigma yx and sigma yy. Okay. Normal force and a tangential force may act in your xy coordinate system for this particular element, ds element, small surface element ds. Okay. So here we can say that this is delta y, this distance is delta y, and this distance is delta x. Okay. And your system, ij system, is like this. So you have suppose u in this direction, and then I and j and v in this direction. Then you can write like this: sigma xx dy or delta y. So let me write this dy, writing dy. So infinitesimally small. Delta is a some finite difference. Okay. So let it be dx dy. So sigma xx dy equals to sigma yx dx. That is nothing but one force balance equation. Another force balance equation can be sigma xy dy equals to not equals this is also not negative, but this is both are positive. Sigma xx xy dy xy dy xy dy, and this is in the opposite direction, sigma yy. Okay, so sigma yy dx, and the n dot ds, since this is having some normal, okay, surface is always represented by its normal orientation of the surface. It can be convex, concave. So that orientation is always needed. N dot ds can be then equals to dy I cap minus dx j cap. Okay. N dot ds can be represented by this. So finally, combining this system, we can write dy minus dx in a matrix form, sigma xx, sigma xy, sigma yx, sigma yy equals to n dot ds, n dot sigma ds. Sigma is a shear stress. Okay, so we can represent this way because sigma this is looking like the same system n dot, only sigma has to be there, then this particular form is nothing but equals to n dot sigma ds. So what does it mean? Control surface, because n dot ds, n dot sigma ds is a surface phenomena, surface integral of n dot sigma ds can be, this is a for a one surface, this is for one surface. So for integrating over all surface, I mean to complete surface, this is over just one element, total surface will be integral of n dot sigma ds. But we also know that control surface integral can be converted into volume integral. So what is the equivalent of control volume integral? N dot sigma ds should be, because of Gauss divergence theorem, it should be del dot sigma, del dot of sigma. You have to disconsider n sigma dot del dot sigma dv. Okay, that is your expression. So body forces, so sigma n dot sigma ds, these are nothing, sigmas are nothing but surface forces. Okay, surface forces, surface stresses, you can use surface stresses. Stress happen at surface. So you can write F surface is equals to integral control volume del dot sigma dv. Okay. So if we add this in your previous equation, you can write d capital phi divided by dt is equals to integral control volume. Now I am writing chi plus del dot sigma dv. You can write like this. But from our RTT equation, from RTT equation or RTT is already theorem, Reynolds transfer theorem for capital phi is equals to mu. Mu means you can write it also like rho u, mass per unit volume. You can write is at density. Phi is per unit volume. I mean, if you defined total volume, so you can write rho u, and phi is equals to u. Then this d phi dt can be written. Okay, so I'm just simply writing here. How we can write it? We can write it like del rho u del t plus del dot rho u u. Okay, dv, and now already we have this chi plus del dot sigma dv. Now we know that this equation is for arbitrary whole control volume. So integrand must be they must be equal. So we can write this equation in a simplified form for constant density, for constant density, for and for arbitrary volume, arbitrary control volume, and for constant density. This equation can be written as del rho u del t plus, so rho can be taken out, and del dot del dot uu can also be written like this, u dot del u. Okay. U dot del u. It can also be written like in this form, u dot del u. Both are equivalent. Is equals to chi plus del dot sigma. Okay. So this is the way we can write. Now this equation was obtained since long back, but we now see that this equation cannot be only solved for u. If you want to solve for u and known rho, you should also know chi. Suppose chi is known, but you should know sigma. Okay, sigma is not a direct quantity. You cannot measure it directly, so you have to measure it indirectly. So somehow we want a relationship between sigma and u. Okay, what do we want here is we want a relationship between sigma and u. Okay, then this whole equation will be in the form of u. Okay, so here we want a relationship between sigma and u, and that is the whole battle. That is the whole battle, and that made these equations not so easy, not so easy. Another difficulty is that sigma is not directly measurable. Sigma is not measurable at all. Okay, not measurable. This sigma is also called as trace tensor. This is not directly measurable. So what is the measurable quantities? The measurable quantity is rate of strain tensor, okay, rate of strain. Tensor. Tensor is a measurable quantity, and that is defined as sigma is equals to half of gradient of u plus gradient of u transpose. Okay. So now you see, we have a relationship between epsilon and u. Now question comes, how we can connect? Okay, so need to connect, then need to connect epsilon with sigma. Okay, sigma is not measurable, but we want sigma in terms of u. But we know that only epsilon is related with u. So now get the epsilon and convert this epsilon in terms of sigma. Can you do that? That was the long battle, and Stokes came into picture. So Stokes is a person. He gave general relationship for homogeneous and isotropic. And isotropic material. Okay. Isotropic means your properties do not change with direction. Properties in different direction, they do not affect. Okay. Like for example, thermal conductivity. Thermal conductivity can be different in X, different in Y direction, different in G direction for some materials. Those materials are called as anisotropic. But for isotropic material, you will have non-directional dependence of the property, so that we can consider it as a constant scalar. So general relationship for homogeneous and isotropic material is given in a tensor form. Okay, so you will have to understand tensor sigma ij. I is running from 1 to 3. J is running from 1 to 3 in a Cartesian coordinate system. Sigma ij is equals to negative PD plus lambda epsilon kk delta ij plus 2 mu epsilon ij. So sigma is connected to epsilon ij through this relationship, and where this PD is your thermodynamic pressure. And lambda and mu, these are fluid properties. These are called as viscosities. Okay, viscosities. So in your undergraduate, you must have heard about only one viscosity, that is kinematic viscosity or dynamic viscosity. Okay, but we have a bulk viscosity. So this is a bulk viscosity, bulk part of the viscosity, and this is your dynamic, kinematic or dynamic viscosity. Now it is a kinematic, it's not divided by rho, so it's a kinematic, it's a dynamic viscosity. Okay, still this is again then we have to see how epsilon kk is connected to velocities. Okay, epsilon is connected to velocities. Epsilon kk has to be connected with velocities. So epsilon is a general term. Kk is the traces. Okay, if you have a tensor of epsilon, it will be represented by a matrix. You should know this. Epsilon xy, epsilon xg, epsilon yx, epsilon yy, epsilon yz, epsilon gx, epsilon gy, epsilon gz. This is a tensor having 9 components. So epsilon has a 9 components, out of which kk components with delta ij. This is delta ij is called as Kronecker delta. K capital Kronecker delta. Kronecker delta. And the Kronecker delta has a property delta ij is equals to 1 when you have I is equals to j. This should be 1 when I is equals to j. So I is equals to j means when x is equals to I, if I is x, y, g, j is also x, y, g, then when I and x, j will become same. Okay, then in that case it should be a 1, otherwise it should be a 0. So it is only considering this these values here, and this ij will consider the rest of the values, all the values. I is running from ijk, so all the values will be considered. But this particular part is only considering the diagonal elements. Okay. This epsilon I, epsilon xx plus epsilon yy plus epsilon gg is also called as trace of this matrix. Okay, and this trace of a matrix is nothing but also defined as del dot u. How this derivation comes, you have to look into too much detail of that. So del dot u is nothing but this thing. If you see this and convert this into vector notation, you know that this is a del dot u, which is equals to 0. Del is nothing but equals to I cap del del x plus j cap del del y and k cap del del z. And u is nothing but I u plus j v plus k w. So you just have a dot product of this. You have a dot product of this, and you will get this del u del x del v del y del w del z. Okay, using the properties of I dot I dot j, I dot k, these properties. Okay, so I will dotted with I only, j will dotted with j only, k will dotted with k only, will give you significant results, and you got this. So in this particular case, for then incompressible, that is only a condition when we got an incompressible flow. So for incompressible flow, this term can be 0. This is equals to 0 for incompressible fluid. Okay, so all the stuff was moving here, and people were, trying to figure out how we can convert this sigma into. Okay, now sigma is also a tensor, so sigma can also be like sigma xx, sigma xy, sigma x, sigma
Sir?
xg. Yeah, time is over.
Sorry to yes, sir. Max sir has started the class.
Huh?
I received a message. I received a message, sir. Max, we have Max class now, sir.
Okay, chalo. Okay then. We'll see tomorrow the next part, next class.